Welcome back to AI.Code.Cast. Today, we're going to be taking a deep dive into a classic algorithmic challenge that has some pretty interesting real-world implications.
Yeah,
The insert interval problem.
it's a good one.
Yeah, so you can think of it like managing a calendar
Okay,
that's packed with appointments,
Right.
and you need to add a new one without any overlaps.
makes sense.
Right.
So it's all about maintaining order within a data set.
Exactly.
It's not just about inserting, but
Yeah.
also merging any overlapping intervals to keep things nice and tidy.
Yeah, so if our calendar has appointments, let's say from 3 to 5 p.m.,
Okay,
and then 6 to 7 p.m.,
got it.
and we want to squeeze in a new one from 4 to 8 p.m.,
Right,
we can't just stick it on the end. We need a strategy
exactly.
to merge it with the existing appointments
Yeah.
and end up with one continuous block from 3 to 8 p.m.
That's exactly right.
Okay.
And this isn't just limited to calendars, This kind of scenario pops up whenever you're working with any kind of sorted range data.
Yeah, that's a good point.
Like imagine managing server resources, allocating memory, or even analyzing genomic data.
Wow.
Yeah, the ability to insert new intervals without creating conflicts is crucial.
Yeah, okay. So this insert interval problem is clearly more common than I initially thought.
Sure.
It sounds like there are multiple ways to tackle this challenge.
Yeah, definitely.
Where should we begin?
Well, let's start with a simple approach that's easy to understand,
Okay.
even if it's not the most efficient.
Got it.
Think of it as our brute force method.
Okay.
We simply add our new interval to the existing list and then sort the whole thing based on the start times.
Okay, so if we go back to the calendar example,
Sure.
we would just add the 4 to 8 p.m. appointment to the list.
Yep.
And then just rearrange all the appointments by their starting time.
Exactly.
Sounds simple enough, but what's the catch?
Well, as you can imagine, sorting a large list can be quite time-consuming. If we have, thousands or even millions of intervals,
Yeah.
this sorting step will become a bottleneck.
Oh, I see.
It's like having to rearrange your entire bookshelf every time you get a new book.
That's a great analogy.
Right.
I can definitely see how that would become a problem
Yeah,
with larger data sets.
definitely.
But wouldn't sorting at least make the merging part easier?
You're absolutely right.
Okay.
Once the list is sorted, the merging process becomes quite straightforward.
Oh.
You can just iterate through the list,
Uh-huh.
combining any overlapping intervals into one.
So let's say we have a list of appointments.
Okay.
1 to 2 p.m., 3 to 5 p.m., 6 to 7 p.m.,
Okay.
8 to 10 p.m.,
Okay,
and 12 to 16 p.m.
got it.
And we need to insert a new appointment from 4 to 8 p.m.
Right.
How would the merging work step by step?
Okay, so first we'd append the new interval, giving us 1, 2, 3, 5, 6, 7, 8, 10, 10, 12, 16,000, 4, 8. Then we sort the entire list by start times,
Okay.
which results in 1, 2, 3, 5, 4, 8, 6, 7, 8, 10, 10, 12,000, 16.
Oh,
Now we can start merging. The first interval at Hyogo 2 stands alone, as there's nothing to merge with.
Right.
Next, we encounter 3, 5,
Okay.
which overlaps with our new interval 4, 8.
Right.
So we merge them, taking the earliest start time and the latest end time,
Okay.
resulting in a combined interval of 3, 8.
So our merged interval keeps expanding as long as we encounter overlapping intervals.
Exactly.
What happens when we reach an interval that doesn't overlap?
Then we add our current merge interval to the final result list
Okay.
and start a new merged interval with the non-overlapping one.
Okay.
So in our example, 6, 7, and 8, 10 would be absorbed into the 3, 8 interval,
Oh, I see.
extending it to 3, 10.
Got it.
Finally, 12,016 doesn't overlap.
Right.
So we add 3,000 to the result list and start a new merged interval with 12,016.
So our final output would be 12, 3, 3, 10, 12, 16.
Exactly.
It's quite elegant how this approach handles any number of consecutive overlaps.
It is, and this sort and merge method has its advantages.
Yeah.
It's conceptually simple and relatively easy to implement.
However, you mentioned earlier that sorting a large list can be a performance bottleneck.
Right.
Is there a more efficient way to solve this problem?
That's a great question, and the answer is yes,
Okay.
especially when we're dealing with a pre-sorted list of intervals.
Okay. I'm intrigued. How can we possibly insert an interval
Yeah.
and merge any overlaps without sorting the list first?
Right.
That sounds almost like magic.
It's not magic, but it does require a bit more cleverness.
Okay.
Instead of appending the new interval and sorting the entire list, we'll scan through the existing list just once,
Okay.
strategically adding and merging intervals as we go.
So it's like finding the right spot in a line
Exactly.
and merging with anyone who's standing too close.
Precisely, we'll be looking for the point
Yeah.
where our new interval should be inserted,
Yeah.
merging any overlapping intervals we encounter along the way.
Got it.
And because our input is pre-sorted, we can do this all in a single pass, which significantly improves our efficiency.
This is starting to sound very efficient, but I'm still a bit fuzzy on the details.
Sure.
Can you walk me through how this linear scan and merge approach works in practice?
Absolutely. Let's stick with our calendar example.
Okay.
We have our sorted list of appointments, 1, 2, 3, 5, 6, 7 of them, 10, 10, 12, 16.
Okay.
And we want to insert the new appointment from 4 to 8 p.m.
Okay, so we have our input, and we're ready to scan and merge. What's our first step?
So,
All right, so we have our sorted list of appointments, 1, 2, 3, 5, 6, 7, 8, 10, 12,016. Our new appointment, 4,008, and we're ready to perform a linear scan. I'm all ears. What happens next?
So imagine we're walking through this list,
Right.
carefully examining each existing appointment as we go.
Hmm.
Our goal is to find the right place to slot in our new appointment
Right.
and merge any overlaps.
So it's like finding the perfect spot in line
Precisely.
without disrupting the existing order.
As we scan the list, we'll maintain a separate list
Okay.
to store our results, the final merged intervals. We'll start by comparing the new interval 4-8 with the first interval in our list, 1 2.
Okay, so 22 ends before our new interval even begins.
Right.
It's like an appointment that finishes before a new one starts.
Exactly.
What do we do with it?
We simply add it to our results list
Okay.
and move on. So far, our results list would be 22.
Easy enough. What about the next interval, 315? That one overlaps with our new interval.
This is where the merging comes in.
Okay.
Instead of adding 3-5 directly to the results list,
Right.
we merge it with our new interval 4-8.
Okay.
The merged interval will have the earliest start time 3 and the latest end time 8, giving us a combined interval of 3-1.
So it's like those two appointments have now become one longer appointment.
Exactly.
And since we haven't reached a non-overlapping interval yet, our results list remains as 22 for now.
Exactly. Now we keep scanning
Okay.
and compare our merged interval 3-8 with the next one in the list. 6-7, what do you notice?
Well, 6-7 also overlaps with our current merged interval, so we need to merge them again, right?
We combine 3-8 and 6-7,
Hmm.
which still results in 3-8 because the end time remains the same.
Okay.
Our results list is still just 12-2.
I'm seeing a pattern here. As long as we encounter overlapping intervals, we keep merging them into our current interval without adding anything to the results list just yet.
You're catching on quickly.
Uh-huh.
Let's continue. The next interval is 8-10.
Okay.
Does it overlap with our merged interval 3-8?
It's a bit tricky. The end time of our merged interval is 8, and the start time of this new one is also 8. Does that count as an overlap?
That's a great question, and it highlights an important detail.
Okay.
In the context of this problem, we typically consider intervals that share a boundary to be overlapping.
So even if they just touch, at one point we still merge them.
Precisely.
Okay.
In this case, we'd merge 3-bit and 8,010, giving us 3,000.
Right, so our merged interval just keeps growing. What about the last interval on the list, 12,016?
This is where things change.
Yeah.
1216 doesn't overlap with our current merged interval 3,000 at all.
Okay.
It starts after our merged interval ends.
Right.
This is our signal to finally add the merged interval to the result list.
So our results list becomes 12,000, 3,010.
Yeah.
And since 12,016 doesn't overlap with anything, we can just add it directly to the results list as well.
Exactly. That gives us a final output of 1,310, 12,016.
Okay.
The same result we achieved with the sort and merge approach, but we managed to do it in a single pass through the list.
This linear scan and merge method is pretty impressive by leveraging the fact that our input was already sorted.
Yeah.
We save ourselves a lot of time and effort compared to sorting the entire list every time.
It's all about choosing the right tool for the job.
Right.
When we have pre-sorted data, this approach shines.
Now, you mentioned earlier that this approach can be a bit trickier to implement correctly.
It can be.
What are some common pitfalls that coders might encounter when trying to code this solution?
One common mistake is mishandling the boundary conditions, like the case we just discussed,
Yeah.
where the end time of one interval coincides with the start time of the next.
Right.
It's important to be clear about whether you consider such cases as overlapping or not.
So it's all about carefully defining the rules of engagement for merging intervals.
Exactly.
Are there any other potential traps lurking out there?
Another common pitfall is managing the merged interval correctly.
Okay.
It's easy to make mistakes when updating the start and end times,
Right.
especially when you encounter multiple consecutive overlaps.
I can see how that could get tricky. Are there any tips for avoiding these kinds of errors?
Clear, concise code is key.
Okay.
Breaking down the merging logic into smaller, well-defined steps
Mm,
can make it easier to reason about and debug.
right.
And of course, thorough testing is essential to ensure that your implementation handles all the edge cases correctly.
Speaking of different implementations, I recall you mentioning something about in-place implementations using Kotlin and C++.
Yes.
Can you elaborate on what in-place means in this context?
So an in-place implementation modifies the original input list directly,
Okay.
rather than creating a new list to store the results. Okay. This can be extremely efficient in terms of memory
All
usage,
right.
especially when dealing with large data sets.
So instead of creating a separate results list like we did in our walkthrough, we'd be directly manipulating the original list of appointments.
Exactly. It's like rearranging furniture in a room without bringing in any new pieces.
Oh,
You're working within the existing space.
that's a great analogy. It sounds incredibly space efficient.
It is.
But are there any drawbacks to modifying the input directly?
The main drawback is that you lose the original data.
Ah, I see.
If you need to preserve the original input for any reason,
Right.
you'll have to create a copy first or use a different approach that generates a separate result list.
It's like the classic measure twice, cut once advice. You
Exactly.
need to be absolutely sure you don't need the original data before going the in-place route.
Exactly. It's a trade-off between space efficiency and data preservation.
Right.
And sometimes that extra space efficiency is crucial,
Yeah.
especially in resource-constrained environments.
Okay, so we've explored the sort and merge approach, which is conceptually simple, but can be slow for large data sets.
Right.
And we've delved into the more efficient linear scan and merge technique, which leverages pre-sorted data to achieve better performance.
Yes.
We've even touched upon the nuances of in-place implementations and the trade-offs involved.
We have.
And we've seen how the insert interval problem isn't just a theoretical exercise. It has real-world applications in calendar scheduling, resource management,
For sure.
and many other domains.
Definitely.
This deep dive has been incredibly enlightening. But before we wrap up, I'm curious, are there any other variations or alternative approaches to solving the insert interval problem that we haven't discussed yet?
That's a great question to ponder,
Okay.
and it's something we'll explore in the final part of our deep dive. We'll uncover some intriguing alternative data structures
Okay.
that are tailor-made for managing intervals and discuss when these specialized tools might be the perfect fit for the job.
Sounds fascinating. I can't wait to uncover those hidden gems. Join us for the final part of our deep dive as we continue to explore the world of the insert interval algorithm. Welcome back to AI.Code.Cast. For the final part of our deep dive into the insert interval algorithm, we've spent the last 2 episodes unpacking different approaches to solving this problem.
Yeah, from the simplicity of sort and merge to the efficiency of linear scan and merge, we've explored the core mechanics and trade-offs involved in handling overlapping intervals.
And we even ventured into the realm of in-place implementations, where we modify the input directly to optimize for space efficiency. But you hinted that there are even more specialized data structures we can leverage for managing intervals.
That's right. When we encounter scenarios with a high volume of interval operations, think constantly adding, deleting, or searching for intervals within a dynamic dataset, we can turn to powerful tools like interval trees or segment trees.
Those sound incredibly complex.
Yeah.
Can you give us a gentle introduction to these intriguing data structures?
We'll think of them as highly organized data structures that are specifically designed to handle interval-based operations with exceptional efficiency. They excel at answering questions like, do these two intervals overlap? Or, find all intervals that contain this specific point.
So it's like having a specialized filing system,
Yeah,
where we can quickly locate and manipulate specific intervals based on their properties.
that's a great analogy. For instance, an interval tree organizes intervals in a hierarchical structure, kind of like a family tree.
Okay.
This allows us to perform operations like searching for overlapping intervals or finding all intervals that contain a point in logarithmic time, which is significantly faster than linear time, especially for large data sets.
I'm starting to grasp the power of these specialized data structures. Can you give me a concrete example of how an interval tree might be used in a real-world application?
Sure, imagine you're building a platform for booking meeting rooms in a large office complex. You need to efficiently manage the availability of each room,
Okay.
taking into account existing bookings and potential conflicts.
So we have multiple rooms, each with their own schedule of bookings. which we can represent as intervals.
Exactly. And when someone wants to book a new meeting, we need to quickly determine which rooms are available for the requested time slot,
Okay.
avoiding any double bookings.
Right. I can see how a brute force approach of scanning through each room's schedule would become incredibly slow, especially with many rooms and bookings.
Yeah, that's where an interval tree shines. It allows us to efficiently search for overlapping intervals, quickly identifying any rooms with existing bookings that conflict with the new request. And if we need to find a room that's free for a specific time slot,
Right.
the interval tree can help us do that efficiently as well.
So it's like having an intelligent assistant that instantly knows which rooms are available and which ones are already booked,
It's
saving us a ton of time and effort.
Precisely. And this concept extends to many other domains where efficient interval management is crucial. Think flight scheduling, hotel reservations, or even analyzing genomic data,
Wow.
where you might be searching for overlapping gene sequences.
This has been a truly eye-opening deep dive into the insert interval problem. We started with fundamental approaches like sort and merge, explored the efficiency of linear scan and merge, and now we've discovered the power of specialized data structures like interval trees.
It's been a journey through the world of algorithms and data structures, showcasing how a seemingly simple problem can lead to such a rich exploration of techniques and solutions.
And it's not just about the algorithms themselves, but also about understanding the trade-offs involved in choosing the right approach for the task at hand. Do we prioritize simplicity or efficiency? Do we need to preserve the original data?
Right.
These are all crucial considerations.
Absolutely. And by understanding the core principles and the available tools, we can confidently tackle a wide range of challenges that involve managing intervals and maintaining order within our data.
So our final takeaway for our listeners, never underestimate the power of algorithms and data structures. They are the building blocks of efficient and elegant solutions to many real-world problems.
And always be curious, keep exploring, keep learning, and keep pushing the boundaries of what you can create with code.
Until next time on AI.Code.Cast, happy coding.